So once you've completed everything, your setup should look something like this. Maybe not the exact thing, but it should be kind of similar. So now you want to get on some sort of an elevated surface, if you know this is kind of tall, and align the rope perfectly so it's perfectly flat, and it makes a right angle with the protrusion, I guess, and take it very close to something stationary. For example, in this case, it's gonna be me just standing, or this phone, and put it very, very close, like this. Now, if the ball comes back and hits the phone, that means the conversion of energy, or at least my experiment, is wrong. I mean, it shouldn't come back, because for it to come back, it will need to get more energy than it started with, basically, and go past it. And also, obviously, if it goes beyond this height, so if it ends up here, it will be the same. My prediction is that it will end up somewhere around like here. No, because of friction, because of loss of energy, due to other factors, with air resistance, because this ball is kind of fuzzy. So let's see. Align it up perfectly, or as perfect as you can get, and do not give any inertia, or do not apply any force to the ball. So just let it go, just like this, and just wait. So clearly, what we can see is that the ball did not really even get close to its original height. Under perfect conditions, however, it would come back to the original height. But as I mentioned, there's some friction going on here, especially since this rope is quite textured, it's quite rough, as well as air resistance with the rope. Since it has a high surface area compared to other ropes, it has these little, threads. And with the tennis ball, which is kind of designed to have a high air resistance with the air. So yeah, that's the experiment. That's all there is to it, honestly. Now we can do a lot of measurements. For example, how much potential energy the ball had here, which is done through the equation mgh. That's the formula. So the h we already know for this experiment, the specific one. Since we are starting perpendicular to the protrusion, we know that the h is just gonna be the length of the rope, or rather, from this, the y difference from this point, or rather from this point to this point, which is 80 centimeters. We already know that. We measured it. We know the weight of the ball as well. It was already weighted. And obviously, the gravitational acceleration on Earth is 9.8, roughly. So now we can calculate it. And with that, we can actually calculate the speed of the ball here, or rather the kinetic energy here. And the reason why this is such a good demonstration is because there are not a lot of forces involved, or at least far less forces than are involved with other experiments. There's not much noise, there's not really too much thermal energy being produced, except for, well, here, not the light, this friction. And it's just generally mechanical, so movement, and potential energy right here, right there, when it's right like that. So at the bottom, it should be the kinetic energy, the potential energy, should be translated mostly into speed. So it should be very similar. I truly hope that the demonstration has truly showed you what the law of conservation of energy is, and also how truly mundane it is. It isn't just some theoretical concept, it applies to every single thing in our lives, every single thing we do, and a simple demonstration like a tennis ball hanging up from a lamp is enough to demonstrate it. Even me walking around would be enough to demonstrate it, or talking. This is also a demonstration, practically, if explained enough, though a far more complex demonstration, obviously. So yeah, if this helped you, very nice. Goodbye.